Welcome to the Simons Institute for the Theory of Computing. My name is Sampath Kannan. I'm the incoming associate director here. I work in theoretical computer science, very far removed from the area of this workshop, but I wanted to give you a brief introduction anyway. The Simons Institute was founded by a generous grant from the Simons Foundation in 2012. And we focused really on theoretical computer science. We try to understand the nature of computation itself, but we try to look at other fields from the lens of theoretical computer science. What can an algorithmic way of thinking tell us about many other fields? That's our general focus. We have been trying to be more interdisciplinary over the last few years, especially. And I think starting from last week, we are launching a big interaction between theoretical computer science and machine learning. Last week, we had a workshop on neuroscience, the brain, and psychology, which went off really well. And this week, we have this great sounding topic on the sciences, the bond between sciences and artificial intelligence. That sounds wonderful. But if you're interested in this general big space, it's a huge space, I understand, which contains many subspaces. The entire following year is going to be in the interface of theory and machine learning. We're going to have a year-long program on large language models, both in the fall and the spring. In the fall, we also have a program called Modern Paradigms and Generalizations, which is also about machine learning in very broad terms. And you might find, you've probably been to too many machine learning conferences because there are too many of those around. You'll find a slightly different perspective here because we are trying to see what theorists can say to machine learning people and vice versa. So we bring together a different mix of people in these programs and workshops. So if you're in the area or you're local, I encourage you to take a look every now and then for the programs. One bit of housekeeping here. This auditorium, surprisingly to many people, does not permit any drinks or food. And that's how we've not had to upholster any of our chairs for the last 12 years. So we want to keep it that way. So please drink and drinks and food outside, leave your drinks out there, and have a great workshop.
Yeah, thanks everyone for coming to this particular workshop. I think once again, thanks to Simons Institute for hosting this. I've been to some of the workshops here before this, and they're really, really nice. So we're very fortunate to have this place on campus where it facilitates some really nice discussions. So this particular workshop, we really tried to focus it on the three pillars of science of biology, chemistry, and physics, and their intersection with AI. I think that's a pretty broad field, so you'll find people from very different backgrounds here, which I hope is going to really facilitate some nice discussions among people, and also some discussions on where the new ML methods are to address some of the big problems in this field. Some very last things to mention is we are gonna on Wednesday have a discussion, a moderated discussion. So if you have any questions and you registered, you should have a form and access to a form to put any questions you might want to get brought up. Bring your most controversial questions because it's gonna be a fun discussion. On Thursday, there's going to be, in the afternoon, some organized social activities so you can just get a feel of what Berkeley is like. Some of those will probably start in the afternoon meeting here at Simons. It'll be a mix of going to the marina or going on a hike or seeing some of the nearby museums as well. And I think that's the main points. Lunch, so there'll be breaks here where there'll be refreshments outside. Lunch and dinner is on your own, so hopefully you can start to get to know small groups of people here and facilitate some of those discussions as well. I think those are those. Oh yeah, and the Simons Institute website, if you look up Simons and Berkeley restaurant recommendations, there's a big list of restaurants based on distance to Simons, so that should help in terms of if you're trying to figure out a place to go. And also working on aggressively. Oh yeah, yeah. So we're so due to the staff length and the strict cutoff of ending the day at a very specific time, we are going to be pretty strict about timing cutoffs. So that's going to be, we're going to really try to run everything on time. That includes for both the longer talks as well as the short talks. Cool. And yeah, without further ado, we'll go ahead and get started right on time at 9:30. I'm very happy to have our first speaker, Tess Smidt from MIT, talking to us about equivariant neural networks.
Good morning. Dee Dee, Jennifer, thank you guys so much for organizing. Simons Institute, thank you so much for hosting. I've also been here for workshops previously, and it's a lovely space, so I'm very excited to be here. So today I'm going to be sharing some of recent research from my group, focusing on using symmetry-equivariant neural networks for applications in chemistry and material science. So I'm over at MIT in EECS, and I run a group called the Atomic Architects that most importantly, we have these little spherical harmonic cow logos because a spherical cow is an insufficient basis for accuracy's sake. So I'm going to first kind of go through what is a symmetry-equivariant neural network, besides a bit of a mouthful, and then talk about some applications. So let's start off. Oh, I also just want to say that the work in this presentation is mostly done by graduate students and postdocs in my group, so a bunch of lovely folks that make doing my job really fun. So a lot of our research kind of stems from the question, how do we build neural networks that naturally handle data from physical systems? So just as an example, a motivating example, let's say I have a bunch of molecules, they exist in 3D space. What are maybe some things that I want to build into my model so that my model doesn't maybe have to learn it, so it can focus kind of more at the task at hand, maybe learning quantum mechanical properties or other interesting things. So, okay. So one potential assumption that we could build into the model that seems maybe somewhat minimal but could be very powerful is building in the symmetry of 3D space. So basically the fact that physics is playing out in this situation in 3D space, how do we build that knowledge into the neural network? So one way in which this is kind of introduced into the data we have of physical systems is that to describe where things are in 3D space, we use coordinate systems. But coordinate systems are fundamentally arbitrary. So I have my molecules. I could use coordinate system 1 or coordinate system 2 to describe this physical situation. And this is the same physical situation, just described differently. And we can always transform between these two descriptions by transforming our coordinate system. And we do this through maybe applying a translation, a 3D translation, a 3D rotation. Typically, we only use right-handed coordinate systems, but you could use a left-handed coordinate system, and that would involve an inversion. So, So one of the problems with this when we want to start, maybe applying machine learning to doing a variety of tasks in the physical sciences is that a traditional neural network has no reason to understand that coordinate system 1 and coordinate system 2 are describing the same thing, just differently. So we have to teach the model basically how to understand coordinate system transformations. And this can be quite both training intensive as well as parameter intensive, because essentially, let's say I have this cube in 3D space with different colored sides. I might need to show it, like brute force show it, the same cube rotated maybe like 500 different times for it to really be able to learn this pattern in different orientations. But there's still no guarantee that, I can't just like rotate it by an itty bit and it's going to still get that it's the same thing. So it's going to be able to learn to emulate, to give the same or similar prediction, but it's not necessarily guaranteed to understand it. But if I build these symmetries of 3D space into the model, I only need to show it one example, and then it can learn to do this in any orientation. And this goes for both local and global patterns. So, that can be helpful. Then you can spend all your parameters learning the science task versus mathematics that we've known for over 100 years. So that's one potential motivation for building symmetry into the model. So this is what we do. We have these, you can either call them Euclidean neural networks or E3 equivariant neural networks. And the main thing is that these neural networks understand without training that if I show it the coordinates from coordinate system 1 or coordinate system 2, it knows it's exactly the same thing, just described differently, or it will have the appropriate behavior in either circumstance. It learns patterns without relying on the coordinate system itself. So any questions before we go forward? All right, coordinate systems for days. All right, great. So one more comment about symmetry. So symmetry is kind of a universal concept, and it's used in many different contexts. So we can talk either about the symmetry of space, where things play out. This is often called the symmetry of the representation. And this is what we've been talking about so far. But there's also a notion of symmetry as like an object possesses symmetry. So if we go back to our benzene molecule, benzene itself actually has quite a number of symmetries. It has 6-fold rotational symmetry, and 2-fold and 3-fold as well. It has a variety of mirror planes, by which if you flip it, it looks the same. It has inversion symmetry. So benzene itself is a highly symmetric object. So this is the symmetry of the object, but this is the symmetry of the representation. And in this talk, we're going to focus on this part, but there are circumstances in which this also matters. But we're going to focus on that. And yeah, I didn't say this in the beginning, but should you have any questions, just feel free to raise your hand. I'd much rather answer a question sooner than have you wait until the end. Okay, so why might this be relevant for this audience? So these types of networks seem to be fairly effective at a variety of ML tasks, particularly in the atomistic sciences. And this is where they've primarily been used. However, they're probably also quite relevant for climate, fluid dynamics, just anything that's in 3D space, really. But atomistic systems is sort of where they've first demonstrated good performance. So you can use them, for example, predicting quantum mechanically accurate properties of molecules, crystals. You can use them for doing molecular dynamics of both small molecules, but also, I really think this is a very cool work. Okay, you can't really see it very well. This is an HIV capsid. And this was done by Boris Kaczynski's group, where they scaled Allegro, which is an equivariant machine learning interatomic potential, and they scaled it to this HIV capsid that's like 44 million atoms. It was a Gordon Bell finalist. So you can basically bring quantum mechanically accurate MD, which is traditionally infeasible at this scale, using machine learning. So that's pretty exciting, pretty cool stuff. Work in catalysis. We have folks from Open Catalysis team here, and we and others have been using equivariant neural networks to predict energies and forces for catalytic systems. Folks have been using it for various aspects in structural biology, whether it's for protein folding, RNA structure scoring, protein-ligand binding, relevant for drug discovery, generating conformers, doing things more in the material science realm of like predicting magnetic structure or vibrational modes, or even generative model tasks. So these have been tasks that so far equivariant neural networks seem to be well performing at, but this is far from exhaustive of where they might be useful. Okay, so for the rest of this talk, I want to talk a bit more about what are the properties that these models have. Like we've talked about coordinate systems and that these things understand coordinate systems, but like what are actually some of the consequences of that? Under the hood, what's different about these types of models, and then how have we used these properties to do some interesting things. And then if we have time, I'll just flash up some open questions. Okay, so these types of models can recognize equivalent recurring geometric patterns that appear in different locations and orientations and even inversions from seeing a single example. And also they can understand the relationship of recurring patterns with respect to each other. So this is a unit cell for a rubidium manganese chloride crystal. It has these octahedrally coordinated manganese atoms. And importantly, these motifs are the same. They're just rotated differently with respect to each other. And we don't just get the global symmetry, we can also recognize the local patterns and the composition of these local patterns so that this octahedron is oriented differently relative to that one. But we only need to see one example of the octahedron to be able to learn to do that. Furthermore, because we have sort of this compositionality of how it learns these patterns, which you largely get from convolutions plus the fact that these models understand these additional rotational symmetries, it means that you're going to be able to generalize well to other materials and molecules that have similar substructures, which is extremely common in the atomistic sciences. We have recurring subgroups, we have recurring coordination environments. So you're kind of able to maximally extract these patterns from a given example. Another thing is that when we're describing physical systems, again, I'm going to stick with atomistic systems because that's what I know best, but this also equally applies to stress and strain tensors of continuum systems. We often are using complex geometric objects to describe the properties of atomistic systems. But the way that these properties or these tensor features transform is kind of non-trivial, especially under these coordinate system changes. So let me give you an example. So on this side, I've got a water molecule just rotating around. And over here, this giant matrix is describing the electron-electron interactions between different atomic orbitals on this water molecule. So the rows and columns correspond to, for example, the orbitals on the oxygen, whether it's be s, p, or d orbitals of different types, and s and p orbitals on the hydrogens. So the matrix is basically saying, is this a favorable or unfavorable interaction between these different orbitals? Okay, so why is this changing? So as this rotates, this basis of these atomic orbitals also changes. And what this ends up creating is that as that rotates, this also rotates, but it rotates in a much more complicated way. Because these aren't just simple x, y, z's, you start having interactions between d orbitals and d and p orbitals. And what's nice is that by building in symmetry, we can actually naturally represent these tensor features with no additional complexity. So not only can we naturally handle the geometry, but we can naturally handle the tensor features that you may want to predict in various scientific settings. Any questions? Yeah, I'm just going to use this. Earlier I said that we're going to mostly talk about the symmetry of representations, but that there are certain circumstances in which the symmetry of the object also comes into play. So just like physical systems, Euclidean neural networks also have the property that basically the symmetry of the outputs also come from the symmetry of the inputs. So basically, if symmetry has been broken, something had to break it. And this was articulated first by Pierre Curie, at least written down in a kind of a nice form, in 1894 when he said the effects, when effects show certain asymmetry, this asymmetry must be found in the causes that gave rise to them. And so what this means is that even without training, if I put in something into the neural network that has a specific symmetry, like that benzene molecule, the output will have equal or higher symmetry. There's no way that a symmetry-preserving neural network can arbitrarily break symmetry. So put another way, if I put in this high symmetry tetrahedron, so just kind of these 4 points that are very symmetric, it's a platonic solid, or this octahedron, another platonic solid with 6 points, and I push it through the neural network, and I have 3 randomly initialized neural networks. And here they're outputting some spatial function in terms of spherical harmonics in this case. You'll see that these all have tetrahedral symmetry, and these all have octahedral. These are random models. So you know from the get-go that this property is going to be there. And this is something that's favorable for many types of training systems. We'll talk a little bit about symmetry breaking if there's time. Just a quick comment about invariant versus equivariant models. So one way you could say that, okay, dealing with coordinate systems is kind of painful, or it requires some extra numerics and computation. What if we just threw away the coordinate system? And this is a completely valid approach. And one thing you can do is describe your system in a way that is invariant. So with features that don't change depending on your change of coordinate system. So you either have radial distances or angles. And this is also like a totally valid approach. Equivariant models keep the coordinate system around. And if the coordinate system changes, the outputs change accordingly. What has been observed empirically, and we can kind of hand wave why this is, but I don't think anyone has necessarily put out a firm theoretical grounding for why this is. But equivariant methods seem to be more data efficient than invariant methods. So what I'm showing here for data efficiency, you typically show the log of the error on your validation set versus the log of the number of training examples. And we see a power law scaling. So in log-log space, it'll look linear. And the critical thing here is we expect that the model will get better with more data, so it should go down. But the thing that's different is the slope. The slope is telling us how quickly is the model learning new information when it gets new data. And we see that the slope is more severe for equivariant models.
Is that for a task that ultimately requires invariance then?
Yes, so it either invariance, yeah, so you can do invariance. This will also work for equivariance if you're deriving the equivariant property through like derivatives. So if you're doing force prediction with an invariant model, but you're taking derivatives of energy with respect to position to get the forces. So even if your output is invariant, like an energy, we still seem to see more favorable data efficiency from equivariant models.
Maybe following up on that, do you mean if you construct something that is equivariant and then at the very end make it invariant?
Correct, yeah. So
ultimately, it's always invariant.
Yeah, so the function end to end is invariant, but you kind of have like equivariant interactions in between, or you have an equivariant representation as your hidden representation. Yeah, and so there's a variety of references. I'm happy I can share slides that I've actually linked in the slides, but not explicitly shown here, that see this on a variety of different tasks. Most of it's energy and forces, again, so that you can actually compare it.
So can you give some intuition as to why this is?
Yeah, so let me show you the next slide. So in some cases, we also see it's a little bit data set dependent as the complexity of the data set, but we also see the higher we go in kind of the types of equivariant interactions that we have, this data efficiency can also continue to improve slightly. So my take on this is that when you're kind of upping the level of representation that you have available in your model, you have a lot more interactions to play with. There's more different ways for your neural network to arrive at a good solution. So there's more degeneracy in your weights. There's more degeneracy in just the different paths that your model could take to arrive at a good solution. You have more flexibility. So that's kind of my interpretation of, I think this might be more of a trainability issue than like can a scale, like sometimes it might be that the scalar function can't represent the task. Soledad Villar has a lot of lovely work under which cases can you and can you not express like invariant functions just using scalars. So I think a lot of it's coming from the trainability and the degeneracy in the weights.
When people have done this, have they looked at like the comparison will be less compute efficient of just data augmentation?
Yeah, that's a great question. So yeah, what do you do in the case of, can you really make a direct comparison with data augmentation? It is challenging to do so. The reason being that like it's hard to find like a vanilla point cloud neural network per se, because just the way that you have to parameterize your convolutional filter for point clouds. There has been actually some recent work. I was like coming across a paper recently that did do a straight up comparison, and it would be nice to see more benchmarks like this. Yeah, I don't off the top of my head, I can't really tell you. Like I have no doubt that with enough TLC in the training that you can get comparable accuracy. I'm not sure the data efficiency will be the same or that the generalization error will necessarily be the same. Like, but I don't think that would be necessarily surprising. Thanks.
How do the higher order interactions arise, and do they require additional computations?
How they arise, maybe I'll go through that a little bit later. They do require additional computations, and that is like a non-trivial thing to discuss that if we have time, or catch me at any break and I will happily tell you all of our compute problems. Okay, so thank you for the great questions. Let me tell you a little bit under the hood what makes these things different from traditional neural networks. So I should first state that the reason why we go to the following steps that I'm going to tell you is because it makes it easier to parameterize the model in a way that preserves symmetry. So we don't deliberately use all this like group representation math to be opaque. It is because it actually makes our job easier for parameterizing the model. But it can seem kind of like a foreign language when first encountering this. I know for me it was. So the three primary ways in which these neural networks differ from traditional neural networks is that we actually start having data types. So we no longer just have numbers running around the network. We actually have these like strict, rigorous data types that are like formally enforced in the network. We have to interact our data differently because of this. And this also impacts how we featureize geometry through, for example, convolutions. So if you hand me a data set and you tell me that it changes predictably under 3D rotation and inversion, then I can provably take your data and break it up into smaller pieces called irreducible representations. And these are the data types of at least the way that we traditionally implement equivariant neural networks. There's many ways that you can do it. This is one of the ways that I find easiest to generalize. That doesn't necessarily mean it's like the most user-friendly or even what's most compatible with modern hardware. So these irreducible representations for O3, so that's 3D rotations, SO3 times inversion, so O3. So instead of the special orthogonal group in 3 dimensions, we have the orthogonal group in 3 dimensions. All of these irreps are indexed by 2 numbers. One number is L, which is a positive integer, and it is an angular frequency. It tells you if I rotate my coordinate system, how quickly does this feature rotate? So if we have L equals 0, we have things that don't change under rotation. So L equals 0 are things like scalars, and I'll talk about pseudo-scalars in a little bit. If it changes at the same rate as a change in your coordinate system, it's something like a vector. So it changes with the change in coordinate system. But then you have things that change more quickly. You can kind of think of this like a Fourier basis, so something that's oscillatory. The next number is parity, which is really coming from this inversion of space. So x, y, z goes to minus x, minus y, minus z. And it gives us sort of like the twins of sort of the normal objects that we get from 3D rotation. So let me give you kind of a specific example. So scalars versus pseudo-scalars. A scalar is something that doesn't change even under inversion. So let's say I'm classifying objects in images. I see a rabbit. If I mirror my image, it's still a rabbit. That doesn't change. But if I'm classifying right hands, and then I mirror my image, it has now become the left hand. So that's not an invariant prediction under mirroring. It changes predictably, right becomes left. And that's actually characterized by a pseudo-scalar. Likewise, for pseudo-vectors, the difference between a vector and a pseudo-vector. So a vector, I invert it, it points in the opposite direction. A pseudo-vector, you actually get these from cross products. So if I take the cross product of 2 vectors, let's say I have a vector along x and y, I take the cross product, I get z. Now let's take the cross product of minus x minus y, I still get z. So it doesn't change under inversion. So rotation axes are pseudo-vectors. And you can get higher order things like double-headed rays or the chiral version, which are like helices. And this is just to give some geometric intuition for what are these weird objects that kind of crop up just as a consequence of imposing O3 symmetry. Okay, so now that we have these, how do we multiply them? So let's just stick with scalars and vectors. So if I have a scalar times a scalar, I get a scalar out. Scalar multiplication, that doesn't change. If I take a vector times a scalar, all this scalar can do is scale the vector. So it can't change the direction. So it's still scalar multiplication. Now I have 2 vectors. How do I multiply 2 vectors? Well, you could say, okay, well, there's multiple options. I could do a dot product, I could do a cross product, but the most general operation is actually an outer product. And this creates a 3x3 matrix because it's kind of the permutation. It's like, what are all the ways I can combine the different pieces to produce a new number? Importantly, this is not a scalar nor a vector, but I can break it down into those irreps from the previous slide. So it can be decomposed. And what I think is kind of fun is that we talked about dot products, cross products. Those are actually things that produce these other irreps. So this outer product actually produces the trace of the matrix, which is a scalar, the cross product, which is the anti-symmetric component, and then what you have remaining is the symmetric traceless component that transforms as that sort of double-headed ray object. So I'm showing you this example to show that like a lot of these irreps are hiding in plain sight. Even if maybe you haven't seen these irreps before, you've probably seen Cartesian tensors, and these things are just a different basis for describing your Cartesian tensors. The other reason I want to show you this is that in most data settings, you only have scalars and vectors. You don't have a lot of data. There's certain cases where you do, but mostly in the wild, you have scalars and vectors. But the thing is, you generate these higher order or these differently typed eReps just by interacting your data, just through multiplication. So in a neural network setting, even if your inputs are scalars and vectors, you can generate this. Another way of saying that is if you restrict the internal representations of your model to only be scalars and vectors, you will never include these interactions. You will not have cross products. You will not have these traceless symmetric matrices. So you're intentionally or unintentionally cleaving off what types of interactions are actually fully allowed by symmetry.
How do we know if that's a good thing or a bad thing?
I always say you got to try it out. Like this is where it's like, okay, you know, I can tell you mathematically what are you allowed to do or not allowed to do to preserve symmetry as to what you should or should not do. That's when training dynamics starts to be like one of the most important things. Or how important is it to you that you can be really fast on modern GPU hardware and easy to reach for compilers. So I think what you should use is going to depend on your situation and your values and your priorities. But I'm always happy to tell you what you can do just by symmetry. Other questions? So to just wrap up this part, so this is now we're going to talk about geometry and how we featureize geometry through convolutions. So just to make it a little bit more concrete, the input to these types of models are going to be geometry. So where are things in 3D space and what exists at that point in space? So you can think of it as a tensor field, if that is a comforting notion to you. If it's not, forget I even said it. So we have these 2 point masses, and they have masses, velocities, and accelerations. So they have different sizes. Those are attached to each thing. The important thing here is that we now need to tell our model, in order for it to preserve symmetry, we have to tell it what symmetry was there in the first place. And so we need to say, okay, the first number in this features tensor is a scalar. And a scalar is something that transforms like the eRep with 0 angular frequency and even parity. The vector, so the velocity and acceleration vectors are 2 different vectors. So those little packets of 3 numbers need to travel together. They travel in packs. eReps travel in packs. So I have a scalar, a vector, and another vector. So now I'm ready to actually give my data to my network. Okay, so what do we do with the geometry? Typically, we're going to use convolution operations to interact the geometry with the features that are living on the geometry. And this is standardly what we do in convolutions, just normally we're dealing with images, so maybe abstracting it as geometry and features. It's a very point cloud way to think about it. Okay, so quick recap on convolutions. We have our filter, we have our image, we slide over it, and we get a convolved feature out. Now, if we're doing atomistic systems, it can be more favorable, more accurate to use points. And so we need to, instead of doing discrete convolution on a grid, we're going to do this over point clouds, where we're going to center. So we have our filter that normally is just a bunch of pixels. We're going to make it a continuous function of the spatial distance. So none of this has to do with equivariance. This just has to do from going from the discrete back to the continuous domain. So I have a filter. This is really a function over space. So we're just going to call it a function over space. And then the way that we center our convolution is a choice. We center it by going to a particular point or atom, and we're going to have certain neighboring atoms, and those will give us our relative distance vectors that we're going to plug into our filter function. All right, so now we have continuous convolutions. What's the equivariant part? The condition that enables our convolutions to be compatible with all this built-in symmetry business is that the functional form of our filter is restricted. So it's restricted and separable to have a radial and an angular portion. The angular portion is actually fixed. So they're a fixed set of functions. They're the spherical harmonics, which are pictured here. And then the radial function, which only depends on the magnitude of the relative distance. That's where we have all of our parameters. That's where all the parameters sit. And this ensures that we can still learn patterns, but in a way that is not sensitive to our coordinate system. So something that's very nice about these spherical harmonics, these are a complete basis for describing angular functions or functions on the sphere, and they transform as specific eReps. So now it's actually pretty clear if we already know how to multiply these different data types, our filter just became something of those data types. And so now when we take our filter and multiply it times our input features, we already know how to do that. All right, so that's kind of my primer. And so I think for the next 30 minutes or 20 minutes, or you want 40 or do you want?
Interleading questions.
Okay, got it, cool. Okay, so let's say no more than 20 minutes so that we can still have discussion. So, okay, so I just showed you how do we kind of build this in, at least at a high level. What does this give us? So these are just going to be some recent applications from the group using equivariant models in different scientific settings. So this is group with Rodrigo's Freitas group, so actually led by them, and then we sort of advised on we were the symmetry consultants, if you will. And so what we did in this project is that Rodrigo's group has these really amazing, you kind of can't quite see here, but these very large molecular dynamic simulations of high entropy alloys. So these are alloys made of maybe 5 different elements that have a lot of really interesting strength to weight properties. So folks are really interested in modeling these systems to better understand what gives rise to these different properties. And so what we did is we wanted to be able to sort of track what was going in these very large simulations. And we made random tensor kernels from our neural networks. We randomly initialized a Euclidean neural network. It outputs a bunch of scalars, so a bunch of invariant features, and when they just use those features to separate out what are the different environments that we have. So it's literally just kind of separating out what are all the unique environments up to rotation and inversion. And so when we did that, we were able to do it just like 10 numbers. It's very easy to separate out these 12,000 unique motifs just through clustering on these scalars. What this allows us to do is it allows us to track the population of these motifs as a function of temperature. So with more temperature, these alloys become more random, so that there's really no correlation between where the different atoms are sitting on the lattice sites. So if this is sort of random, this is like the melting point over here, we have some short-range structure here where different populations are more prevalent than others. And so we can actually characterize when there's chemical short-range order. And then furthermore, we can kind of correlate which local environments cause kind of the most strain in the lattice, which is going to be relevant to a variety of its mechanical properties. So that's just using an untrained features from this network, just predicting a bunch of scalars. So that was a fun project to see how we could use this just to efficiently analyze these complex simulations. This is a project with Meta, Open Catalysis team. We got Abhishek and Brandon from the team, and my grad student, Elin. And what we did here is, so Elin was really curious when he came to my group about how could we take all of the kind of successes of like transformers and other types of advances in NLP and computer vision, can we port them over to the sciences, but while adapting them to be symmetry-equivariant? And so equiformer is the merger between a transformer architecture and equivariant interactions. And Elin was really, really careful as to how to actually translate this over while maintaining expressivity. And so the first version of that was equiformer, and then working with Abhishek and Brandon, we did equiformer v2. So this essentially has an attention mechanism that involves tensor products and all the different interactions that we spoke about. And it's trained on the open catalysis data sets. So here I've got some examples from the 2020 data set, but it's also been trained on 2022, and also the open direct air capture data set, which is a MOF data set. And equiformer v2, at least last time I checked, is currently state-of-the-art on all these benchmarks. It can be kind of a big model, so you can scale these up with enough compute. And I think what Elin was especially interested in is like what happens when you take an equivariant model, you train it on a big data set. Can it be effective at complex science tasks? And so far it seems like there's a lot of good indications that that's the case. One key thing that made equiformer v2 work is that there's a really cool operation developed by Larry Zitnik, also at the Open Catalysis team, where there's a there's basically a really neat trick you can do in the convolution that makes it much more computationally efficient on modern hardware. And that's what's allowing Equiformer to actually scale to like L equals 6 to L equals 8, whereas a lot of current equivariant models are more at like L equals 2 or 3. So that's a really key innovation. So a lot of interesting stuff going on in this space for different ways of scaling these methods, but I wanted to just highlight that. Okay. So this next example, it's going to be much more material science-y, but one of the reasons why I wanted to show it is that this is a place where, okay, we're working with equivariant models and stuff, but actually the key thing that makes this application work, this is going to be for vibrational properties of materials, is actually plugging in physics formalism at the right point. So figuring out what's an easy thing for like an ML model to predict versus what's the quantity that we actually want. So what we're going to be doing here is we're going to be talking about, I have some sort of neural network, invariant or equivariant, that models the energy of a system. I'm going to take derivatives of that energy model to get a variety of properties. So I can take derivatives with respect to position and get forces. In this case, I'm going to take a double derivative with respect to 2 different positions to get basically vibrational properties, which isn't observable, actually. You can actually use Raman or infrared spectroscopy to measure vibrational properties, whereas it's pretty hard to measure forces. Yeah, like nearly impossible to measure forces directly, but vibrational properties you can access through a variety of spectroscopies or neutron scattering. Okay, so this is the quantity of interest. Vibrational properties of crystals are a little bit more complicated than molecules. We also do it for molecules, but in this setting, I want to just focus on the materials case. So we have these band structure diagrams, and this is energy. And then this gobbledygook here is actually a 3-dimensional path in reciprocal space or Fourier space. And it's essentially describing different distortions of the crystal lattice induced by these vibrations. So it's kind of a complicated property. It's a continuous function of a 3-dimensional variable k. So you kind of think, how in the world am I going to structure this as a machine learning task? Like, is it an image? Like, how do I produce this continuous object? And this is where physics formalism can really save the day here. So there is this thing called a dynamical matrix, and I'll walk you through the form. And essentially what we can do is we can take something that is relatively straightforward to predict with a graph neural network. We can take an edge prediction, or basically what becomes an edge prediction, which we take the energy that we predict and we take derivatives with respect to 2 different positions. So for example, these 2 positions. And that's pretty easy to get because, okay, we already know how to do derivatives from the energy. Great. So how do we then get to this continuous function thing? Well, it turns out that once you have what are called these force constants, you can get the dependence on Q or K, this it's called like the reciprocal momentum, and you basically get these phase factors. And where these phase factors comes from, it's something that you would cover in a solid state physics course. But essentially, you can just plug in these phase factors, and you're able to turn your edge features from these derivatives into this continuous function. Now, you have to do this correctly. You have to do it in Jackson. You have to think very carefully about how you're taking your derivatives. So don't do a naive Hessian. Use a vector Jacobian product. So there's some implementation details. But by doing this, we have a lot of really nice guarantees for how this works. So to make the diagram, there's one more step. So this gives you a big honkin' matrix. The way that you actually get the bands is that you take the eigenvalues and eigenvectors. And so what you're seeing here are actually, for a given Q, what are the energy eigenvalues? For this Q, what are the energy eigenvalues? So that's one way you can take something that like previously, like how in the world do you predict something like that? Use a little bit of just a smattering of physics formalism. And you can actually get a very natural prediction from a neural network. So here's actually examples of, we have kind of the training curve in blue, and then this is the test curve in black. And I'm just going to arbitrarily divide it up into like the best third, the middle third, and the bottom third. And these are examples of the different band structures. What I want to point at is there's a lot of structure of what things overlap or what things cross in these diagrams. And what you'll notice is that the only thing these diagrams are getting wrong is where exactly the curve should be. But the actual form of the curve, and even the curvature of some of these curves, is correct. And that's because a lot of this stuff is just determined by symmetry. But this isn't coming from the symmetry of the energy model, although you do need that. It's coming from the symmetry of how we built the matrix. So because we use the physics formalism, this becomes a much more tractable task. So I think like placing the right amount of science in the right places, like really leaning on your formalism, can make this a much more tractable task. So this is trained on a variety of 100 different element types. And the good answers are like pretty spot on in terms of accuracy. And even the bad answers are still somewhat usable. Like it would still tell you like what range of energies you should be looking at for different experimentally accessible probes. Okay, I'll skip this part, but any questions on this? Yes.
And one question, what happens when you step away from high symmetry directions and positions in Q space?
Yeah, so
Models are usually good in high symmetry positions, right? But
I don't think the models are necessarily good or bad in any symmetry positions. It's just more of like it will have the correct symmetry at those positions.
But like modes, for example, split apart when you step away from.
Yeah, so you're saying there's more like energy degrees of freedom?
It's more challenging, right?
Yeah, so the way that we're fitting things is through force constants. And so it's not, yeah, so you can train, like, there's different ways to train these sort of things. In general, we're training these just on forces and then just seeing what comes out. You can also train on second derivative data for force constants. I would say if you're stepping away from high symmetry points, I think it really still comes down to just the accuracy of your force constants, because that's really what's driving the predictions ultimately. So certainly, I think if you have certain discrepancies between certain edges, I'm sure there's specific patternings of that that's going to aggravate more of far away from high symmetry. But I don't think from the way that it's kind of formulated here that high or low symmetry situations matter too much. I'm sure that, yeah, I don't know, that maybe I'm not having the right intuition about it, maybe I'm misunderstanding the question, but I'd be happy to chat about it. Okay, so let's talk a little bit about some generative models. So one thing that I find really exciting about equivariant models is that it really allows you to play with geometry, because you still have geometry as like a faithful data type in the model. And this is an autoregressive model that we made called Symphony. And Symphony, so autoregressive meaning that we're going to build up, for example, a molecule one atom at a time. Doesn't seem like the most efficient way to build up an atom. But the key thing that we were interested in with this was whether or not we could use kind of equivariant distributions to predict where atoms should go. So let me kind of walk you through it. So our target is to build up a molecule one atom at a time. And we'd like to do this kind of using these equivariant features. And so what we do is we start with an unfinished molecule. It could even just be a single atom, maybe like a hydrogen or something. And we embed this kind of context into the model through kind of a standard neural network. And then what we're going to do is we're going to ask the fragment, who wants a neighbor? Who feels like they're missing a bond, or they're missing an atom near them? And so the atoms will basically vote saying, okay, I need another neighbor. So then we'll sample who's going to generate, which atom will be generating the next atom. And then we say, okay, well, given that this atom circled here will be generating the next atom, what type of atom do you want? Do you want a hydrogen, a carbon? So we sample that. Then from there, we're actually going to use these distributions articulated with spherical harmonics and radial distribution functions to really efficiently articulate, okay, it wants the hydrogen atom here or here. And so we can do this very efficiently. Now, we did this in an autoregressive setting. This works very well for like small molecules like QM9. So it's better than just using invariant models that use like a triangulation procedure that requires all the atoms. And it's like competitive with some diffusion models. I think diffusion models are still a bit better on accuracy because of a particular way we did our radial functions, but I think we can overcome that. But what gets me really excited about this is that we did this on just single focuses, but with enough sampling and conditioning, you could potentially do this on multiple atoms at once, multiple environments at once. So it might be kind of a really interesting way to scale up geometry in an efficient manner. So this is kind of something fun you can do when you have equivariant features. You can very efficiently articulate positions of new atoms in a way that preserves permutation symmetry. So locally, when you sample, you're kind of breaking permutation symmetry in a way because you're like doing a sampling procedure. But this distribution in itself preserves permutation symmetry, which is kind of nice. Another kind of more generative model type thing is that so this is working with Joe Jacobson's group at the MIT Media Lab. And Alan Costa has really been driving this project in Elon. And this is an autoencoder context where we were wondering, can we basically trade geometric degrees of freedom for feature degrees of freedom, kind of in the way you would do with like a U-net, but now we're doing this in a point cloud setting. So we have a protein structure. It has this native backbone. And what we're doing is first we're encoding kind of the all atoms onto the alpha carbons. And then we're using convolution with a greater than 1 stride. And we're just coarsening 3 residues at a time into kind of new coarsened residues. And then we do that again and again and again. I think this was like 100 residues, maybe more, until we have a single point with a lot of tensor features. So instead of having lots of geometric degrees of freedom with some features, now we have no geometry and tons of tensor features. And then we go back. So just a standard autoencoder. It's not variational. The only type of additional loss we put is that we wanted the tensor features to not collapse onto each other. So we wanted to minimize the dot product between these different objects.
Why do you need to do that if you're trying to just get the reconstruction?
I think we found the reconstruction to be a bit better to do that. I don't know if you need to, but it is something that we did. But it's an interesting question. Okay, so now we have these latent encodings of these proteins, and we're wondering what are some of the ways that we can do this. So we can reconstruct the proteins, but the thing that's really cool in my mind is that if you take proteins that, let's say, kind of open and close, maybe in a non-trivial way, and you just interpolate between the endpoints that we have through crystallography. So, we can only see certain things in crystallography. It has to crystallize. So suppose we were lucky enough to crystallize 2 different modes of the same protein. And then we say, okay, let's interpolate in Z. Does this look even like a valid protein structure? And it turns out if you do the interpolation in Z, it actually does look reasonable. When you go ahead and look at the statistics, you decode it back out, and you look at the statistics of the bond lengths and the torsion angles and all these sorts of things, it actually does look physical, versus if you did it in the original coordinate system, it would look like gobbledygook. It would not be physical at all. And so we've done this for several different proteins for which you have sort of multiple configurations. And it looks like in this interpolated space, it's doing something that looks rather physical, which is, I think, surprising, given how little requirements we put on the latent space. We just said, don't put your tensor features on top of each other. And it's an equivariant model.
So the interpolation is not coming from the autoencoder? Where's the interpolation?
So we interpolate in Z
Yeah.
and decode for each kind of step in the interpolation. Yeah, so the autoencoder, its purpose is just learning Z. So we will encode the initial and final structure into Z with the encoder, but then everything else is just using the decoder. So I think there's, another thing you can do, this is not necessarily like the best way so far of doing it, but you can actually do a diffusion model on Z and generate out new protein structures. And you'll get things that look decent, but I think there's a lot of improvement here, and we have some ideas for how to do that. But it is at least kind of interesting to see that you could start, instead of doing like all atom generation for proteins, you can just do it on this kind of these diffusion over the tensor features and then get your all atom coordinate system out afterward. But I think back on this point with the interpolation, I think what's really interesting is it's suggestive that equivariant models may be very effective at coarse graining. And not just coarse graining to like new scalar features, but if we're coarsening, we're trading out these geometry features for features on new geometry, kind of in the same way that you would coarsen for like a UNet or something, but doing it in the point cloud setting. It suggested that the tensor features are actually really helpful for doing this. So I think there's a lot of interesting avenues to explore on that front. Yeah.
Have you looked at like not going all the way just in one side of the trade-off, but like maybe keeping some of the geometric features and seeing if it performs better or worse?
Yeah. I bet Alan and Elon did some of that, but I don't have that information off the top of my head. I don't know if it's actually, it might be in the SI for the paper, but if I don't know, I can get you to the people who would know. Yeah, thanks for the question. Okay, so making sure that I don't go too much over time. Last but not least, let's talk a little bit about symmetry breaking. So there are circumstances in which you may want an answer that has lower symmetry than your inputs. So let's say I have a square and a rectangle. I'm looking at Alyssa right here, who's on these works. So I have a square and I want to turn it into a rectangle. And I hand it over to an equivariant neural network, in this case in 2 dimensions. What you're going to get is you're going to get something like this. And this is kind of puzzling because it's like, where did it get the other rectangle from? I only showed it this rectangle. And what is happening here is it's because this rectangle is implied by symmetry. So if this is a valid answer, then by symmetry, this is also equivalent because it's the same modulo rotation. And so the model is incapable of breaking symmetry, but the closest answer that preserves symmetry is to give you a linear combination between these 2 answers. So that's interesting. However, I really just wanted one answer. So how do we overcome the fact that, like, this is doing good things for the right reason, but there may be still circumstances where I want this answer, or maybe both answers. So what are some ways to do this? So one way, and this is the paper that Alyssa's on, and this is with Robin Walters at Northeastern, and Ray, Robin and Ray worked a lot together, and then Ray was in my group for a bit. One way that you can do this is that, something that I didn't explicitly say, is that in most equivariant neural networks, our weights are restricted to be scalars. This kind of intuitively makes sense because anything that's not a scalar is breaking symmetry. So the weights in the model are scalars. If you have non-scalar weights, so things that transform not as an even parity L equals 0 object, it's sort of preferentially choosing certain directions. But if you want to lower the symmetry that the model preserves, you can have non-scalar features. And this allows the model to learn one solution. So in this case, something that's really neat is that we proved a while back that the gradients of these models also have certain symmetry properties. And so you can actually have these models only learn the minimum amount of symmetry breaking necessary to accomplish the task. So in this particular task, you only need to have an L equals 2 symmetry object. And this will allow you, given this input, to give you this output. And it is able to learn that single solution. If I went ahead and rotated these non-scalar weights, I would get this answer. So that's one way. So you can kind of learn to break symmetry from training. And that's a powerful technique. Another thing that you can do, and this is with my student Yuqing, is we kind of ask the question, well, what's a way in which we can generate the set of solutions induced by this symmetry breaking? This particular work is much more about proving the bounds for how easy or hard is it to articulate these sets. But essentially, in this circumstance, you can derive what would be the set for going from the rectangle or from the square to the rectangle. And there, you have these like 2 double-headed arrow objects. Yuqing derived this for a variety of arbitrary groups. And this would be a way such that if you gave it the first object, it would predict one of them. And you gave it the second object in this symmetry breaking set, you'd get the other one. So this is just some potential ways that you can handle symmetry breaking in a rigorous fashion, either through training or kind of through more of a mathematical approach. And this is useful for things like crystal phase transitions or arbitrary environmental parameters and like fluid dynamics that maybe you can't directly observe, but you want to be able to treat. Okay, I'm going to wrap up there. Open questions, I'll just hit them really quick. Equivariant nets can be slow. This is very much a compiler and a hardware problem, super interesting. Lots of opportunities in generative models. We still don't know the best ways to construct these types of architectures, so there's a lot of room for what types of operations we could invent using these basic building blocks, and what's the best practices for training these. I want to thank, again, my group for all their hard work. I want to thank our amazing collaborators that we've just really enjoyed working with. Our funding that helps us keep the lights on and keeps all the grad students fed. And I'm going to leave up these take-up slides, and I'll take any questions in the remaining 5 minutes that you might have. I'll take here and then here.
So when you were talking about,
We're gonna use the mics for the traditional.
You were talking about irreps and sort of the interesting types, right, that you needed to represent within the neural network.
Yeah.
It really reminded me of the work on Clifford algebras in neural networks. Is that like a way that you think about implementing this kind of thing with multivectors, or do you sort of have a quite different kind of implementation in practice?
Yeah, okay. So first of all, I'm largely unfamiliar with Clifford algebra. That's sort of like the differential geometry view of rotations, and I've always been stuck over in group representation theory. So I'm sure there's like some beautiful connections between them, because like typically Clifford algebra deals with differential forms, so like bivectors and things. You can interconvert some of them. But I think it's much more like the Cartesian construction versus like the irrep construction. And I think as far as determining how to construct equivariants, I'm less familiar with how those constraints look in that formalism. I'm much more familiar with how they arise kind of in the representation theory formalism. So I don't have a good answer for you. I'm sure it's a great way to think about things. I've never learned Clifford algebra.
Well, specifically things like pseudo vectors wind up being bivectors in that algebra,
right?
For example, and so that's kind of what called it to mind.
Yeah,
right? Is that then the tensor products are these multi-vector objects?
Yeah. So I would say that those objects are not irreps, but there exists a change of basis between kind of those types of how many times you're producting vectors, kind of a Cartesian setting, or like you said, the bivector setting.
Yeah, thank you for this very nice talk. In one of your parts, in one of your slides, you talked actually about a generative process for, I believe, bonds or molecules as they slowly build up. And that was actually very interesting. I was wondering, in the fusion models, right, you have this notion of a temperature. I know your model was sort of autoregressive, but in the fusion model, you have like this temperature that you slowly cool down. I was wondering, can we learn, would it actually make sense to think about generative processes that sort of mimic that cooling process, that you basically not sort of, that you sort of essentially include the bond strengths, I guess, like, or if you take a molecule, you would heat it up, which bonds would break first, and then sort of trying to reverse that process.
Yeah, so I mean, one interpretation of kind of your comment is there's no reason why you can't combine sort of autoregressive and diffusion like elements together. There is a notion of temperature in the sampling procedure here, actually. So it's sort of like it's like a Metropolis Hastings sort of thing. So like you have certain probability distributions, but like how often are you going to sample something that's less likely, maybe at equilibrium? So there is a notion of temperature there. I think one thing, and I think what you're getting at here is like, once you've put a position in there, it's kind of frozen. What if then you generate somewhere along the line that's like, oh, this kind of wants to like bend in a little way? So that's where I'm kind of thinking like it could make sense to have sort of like a, adjustment step. We played around a little bit with it, and we didn't get too far, but we were sticking with just QM9. And I do wonder for like larger molecules, how often would you kind of need to readjust? Because one of the unit tests that we use for this model are platonic solids. And it's really interesting once you get up to like the icosahedron, which is like 20 vertices, all these little errors start accumulating, and you have the cage doesn't like quite close. So that kind of indicates that could also be kind of a problem with just fixed settings. So again, it could be nice to have things be able to move around a little bit more like a diffusion model.
That sounds good, right? Yeah, I'll follow up with you offline. Thank you.
Sounds good. Thank you. Okay, questions? One more minute.
A great talk, really interesting. I have a generic question that maybe you can answer. So, when we think about like equivariant representations, it's clear that at the end point, in many cases, we will want equivariance. What's less clear to me is that during optimization, you want it. I'm wondering if you have any thoughts about like whether or not optimizing in the equivariant subspace is actually advantageous.
Yeah,
Like,
no, this is a wonderful question.
Make more sense to just post-process and make everything equivariant at the end, or?
Yeah, so I think there's a lot of different arguments kind of either way. I think that this is something that with Robin, one of the collaborator on one of the symmetry breaking things that we've kind of discussed a lot, is how do we even go about measuring like how restrictive is equivariant? Because it's in some ways it's extremely restrictive on just even the structure it induces on the vector spaces. Like it's a subtle but very heavy-handed assumption to build in. We've done some preliminary explorations about, like Alyssa's been looking at, like if you initialize things to be like kind of almost equivariant, how easy is it to pull it back onto the equivariant manifold? So I don't have any answers for you. I do think that this is something that should be empirically investigated, and from both sides of like, let's relax equivariance this way and let's see like how, like, but the way that equivariance typically manifests, if you look at like Chris Olaw's work and friends and like their convolutional neural networks, the way that they tend to learn features, like it tends to be like a filter bank, which is very much like the group convolution view of equivariance. It's not really learning like these types of vector spaces, because the operations that kind of vanilla networks are built from cannot articulate the types of, like, you can't go from that operation to the types of operations we do. Like, just operationally, they look different. But there might be like an interesting way to make that more flexible. So I think it's a great question. I think really empirically going after it would be kind of the right way to try and settle this, or to like gain some insight from it. But it's very much worth doing.
Thanks.
Actually, maybe I could do one follow-up to Grant's question. What about, so a lot of that is within the framework of equivariant neural networks. What about training going the other extreme we've seen data augmentation actually works really well in many other fields of ML. We've now seen it works quite well with proteins.
Yeah.
Do you have any thoughts about how that compares?
You're talking about like AlphaFold or?
Oh, yeah, AlphaFold is the most recent example.
I was waiting for the AlphaFold question. Yeah, so I think, like I said, I think if you're willing to spend a lot of effort in carefully training your model, and you're happy to have a lot of additional parameters, like it's much less parameter efficient. But if that's fine, I think it kind of goes back to your values. I do think that the equivariant representations, like the hidden representations, are interesting into themselves. Like even if they were not as effective as data augmentation, I would still find them really interesting for reasons like just this interpolation that you get in that like autoencoder latent space for proteins. It's like, who ordered that? Like I don't have a good sense of like how much data augmentation you would need for that interpolation to be smooth. Maybe you could, I don't know. So I think it's a great question, but I don't necessarily like have much intuition.
I have a quick follow-up to Aditi's. Like, it seems like in the modern era, we're trying to be the least parameter efficient possible.
Yeah.
So
yeah, I get that impression too.
So I'm a bit confused.
So there's where the part where it's like AI for science. What does it mean? So it's like, are we trying to build things that explain the natural world to our puny human brains? Or are we just looking for the thing that's going to get us to a good enough answer for us to optimize things well? And both are extremely, I think, valid pursuits.
Clarification, because Grant also used this word optimization. I didn't understand optimization of what? In what context?
I think of the model. So like the training process.
Like
I
the
see.
Training to fit process, the model.
Like, is it a disadvantage to basically only be able to optimize on an equivariant manifold
I see.
Versus to go from sort of like a less constrained or a differently constrained, because there's still constraints on the manifold for like a vanilla neural network, but it's a very different type, and it's a manifold that we're much more practiced at optimizing over.
Is there any way to relax it and sort of slowly tighten it?
Yeah, so we've started looking at this
okay.
a little bit, but the thing is, it's actually kind of hard to do the interpolation between equivariant architectures and like the types of kind of vanilla neural networks, and I'm using this very loosely, of what vanilla neural networks mean, how do you actually do that interpolation? Because structurally, when you look under the hood, the way that matrix multiplies are happening is very different. Like the pattern's very different, and also just, yeah. So it's a little hard. Ideally, you would just continuously interpolate between your model architecture, and I don't know if we have a way to do that yet.
Could you ensemble like a one that's not equivariant with one that is and reweight that?
Yeah, I mean, there has been success actually. Like, so when we submitted the Equiformer architecture for the open catalysis competition, we were second place. The first place was an ensemble model that actually, I mean, it was a bunch of like equivariant and invariant networks, but like, there's no reason why ensembling wouldn't be just as effective in this context as it is in other cases. I think it's just what you want. I don't want to ensemble models, but that's because like I'm a stick in the mud, you know. So it's like I just want it to be like pretty and
totally
nice.
Understandable.
But I will, you know. I think other people should feel free. I should feel
that's why we invited you, because you don't want to just ensemble the models. So that's why
I'm totally fine with other people doing it, but I'm just like that. I just
offense
can't.
to anybody who may have
no
done
offense.
such a thing.
No. Like I recognize this is like it's like, you know, when you play a game, right? You play a game, there's arbitrary constraints, and that's what makes the game fun. Like cheating isn't actually fun when you're playing a game. The reason is to try and do arbitrary goals through arbitrary means, and research is kind of like that too sometimes.
All right, I think we're into our break. So it was a half-hour break. Now it's a 25-minute break. No. It's fantastic. No, it's great. It was not blaming you. If anything, it was me and Aditi who made it go over. So that's why we did it. So we'll be back here at 11, and Anshul will tell us some fantastic biology.